Hello, this is the lecture on automatic face recognition, similar to the previous lectures on iris and fingerprint. We're now to focus in one of the most important biometrics used nowadays in smartphones and many different applications. So similar to previous biometrics, in this case we will have as input biometric, as input information, a face image or a face video. And then we can have either a verification or an identification system. So in an identification system, we will have a search database or a reference database composed of a number of identities, labeled identities. So this is a reference dataset, and we will perform for identification and one-to-n comparison in order to find the best match or a ranked list. Is face recognition difficult? Yes, it's difficult, mainly because when we capture a face, there are many variability factors that really affect the information, the biometric information that is stored in the system. Variability factors in the style of the facial hair, some objects like glasses or other occlusions, the facial hair also in the bird, makeup, facial emotion or expression. The mouth can be open, some gesture, also the pose, illumination, everything makes that when we interact or when we are acquired in a face camera in an environment, then really the information stored can change dramatically depending on these conditions. So we have to find really distinctive and stable patterns in these complex images. There are many variability factors to deal with in face recognition. So usually face biometrics are divided in two main face biometrics in two main blocks. The first processing block usually is face detection. It's kind of segmenting, locating the face to recognize in a given image. And this problem usually it's much more difficult compared to what is fingerprint segmentation or iris segmentation. Remember, we discussed already fingerprint segmentation. That was just 1-2 slides, very minor detail about how to segment a fingerprint because it's not that hard. Fingerprint inside fingerprint image is well located, so usually applying very simple methods based on the orientation field, you can really segment very well a fingerprint. That happens also in iris. In iris, we have very good methods to locate the iris boundaries. In face, we have to locate the face usually in a very complex image. In a background, sometimes this background is cluttered, the face may be at a distance area. So we may have to really use a very sophisticated method, very complex method, sometimes as complex as the recognition, just to locate the face, to detect the face. And then after we detect the face, we have to align and to normalize in order to have the face like in a image patch that we have controlled in terms of position, location, orientation, and so on. So that's the first problem in face detection. And face detection is a particular a scenario of general object detection. In fact, with Alvaro, you saw many techniques for general people detection. So to detect a person in an image, to detect a person in a video sequence. Similar techniques have been developed for general object detection tracking. So these kind of general techniques for object detection can be applied here to face. Typical or traditional techniques for face recognition are Viola-Jones algorithm. This is very popular and is already implemented in many software SDKs, software tools for computer vision, like OpenCV. Also, MATLAB has a Viola-Jones algorithm for face recognition. And these kind of algorithms are based on multiple classifiers and some kind of texture features, like hard features. So these kind of detection algorithms help us to detect the face or several faces in an image. Most advanced methods for face detection use deep learning. In fact, deep learning as applied to face biometrics, both for face detection and face recognition, is clearly the state of the art and superior to any other techniques in face. This not happens in fingerprint recognition or iris recognition. Previous lectures on fingerprint and iris, you saw that we developed handcrafted methods that are very specific for fingerprint processing, the orientation of the ridges, or for iris processing, for processing the particular boundaries. There were particular methods handcrafted, very detailed and very specific for those biometrics. For face, general methods developed for general image processing, general computer vision, apply very well here, and in fact are clearly the state of the art. And this happens also with, especially with face detection. So general object detection algorithms are applicable and work very well for face detection. So we will have the first stage. From the general image, we will have to detect the face, and this is related and of course dependent very much on the scenario. For example, in this kind of surveillance images, the distance to the camera usually is long, so the face usually has to be found like in a large context. For a selfie picture, for example, then we will have most of the image will be the face. So segmenting properly the face is very different depending on the scenario and the camera. And then when we have our face located, we will recognize. So recognize means we will extract features, construct the biometric template, and then compare templates. So that's the same as before. So as I said, suppose we have already detected the face. We have a database of pre-enrolled people, identities, based on face images, face templates. And then we will pre-process, sometimes enhance the contrast, image filtering, cleaning, and then we will extract some features, and then we will classify. We compare with the enrolled template, and then in an identification system, the result will be a ranked list, and perhaps we take just the first one, the first candidate, and then we find a match in the first place, the rank 1. So we are going to see 3 different generations of face recognition algorithms. This is face extractors, face feature extractors, and face matchers. So first generation is around 90s, second generation 2000s, and the third generation, which is basically the last decade and currently, which is clearly dominated by deep learning in case of face recognition. And deep learning is so superior, as much better than the other ones, that the first 2 generations really are only studied for historical purposes, not because you're going to really find these kind of applications in real work and practice in real world systems. So deep learning is so good and so fast and so accessible, because there are open source implementations for deep learning applied to face detection and face recognition, that it's no sense to really go into much detail into these old methods, only for historical reasons and for learning reasons, not really for real practice. Practice, we are clearly here. For the third, for the second laboratory on face recognition, we are applying these very basic methods, eigenfaces, feature faces, because in this course on biometrics, we don't want to go deep into deep learning. So deep learning has many tricks, and for us it's a kind of advanced topic, and we are not going to really play with deep learning in the course. The the purpose of this biometric course is more into the general aspects of biometric system, the errors, the how to evaluate a system, the quality effects that you find, how these quality effects affect the performance, how to estimate these score distributions, and then for some modalities like which are very important, like fingerprint, iris, then really to have the intuition of what are the modules working inside. So for face recognition, just keep in mind that deep learning, especially convolutional neural networks, are the state of the art, or variations of convolutional neural networks are clearly the state of the art and much better than the other approaches. Just then, for historical reasons, I briefly introduce first and second generation, these basic methods and these kind of more advanced methods applied to face recognition. First generation in the 90s, which was basically the beginning of face biometrics. The first, I would say, seminal work, pioneer work in face recognition was Eigenfaces, 91. That was very simple method, really. It was basically taking an image represented as a multidimensional vector, of size equal to the number of pixels, and then taking that vector, let's say number of pixels is the size of the vector. We put that vector in a multidimensional space, and then we project that vector to a subspace, linear subspace. In that subspace, what we try to find is the best representation of that initial face image without considering any other elements, just the subspace of less size that represents best the initial image. In that size in that subspace of a smaller size, then we can directly compare faces using Euclidean distance, for example. And that approach had many limitations, but at least worked. If the images were properly aligned, for example, no much noise, no pose variation. So if the images were controlled, then it enabled face recognition just by projecting to a linear subspace. It was a direct implementation of a very popular method in statistical analysis called PCA. So we project and we basically perform principal component analysis, PCA projection, over the face images, directly the face images with that, just that. Second, a kind of evolution of that was considering different samples, different faces from the same person to construct a specific matrix, a specific scatter or a kind of a cloud that represent a specific subject. Imagine just intuitively that a subject in some space is represented by this kind of cloud. So if and that cloud represents the variability of that subject, the images of that subject. This way we have like a mathematical representation in a specific space of the variability of the subject across different dimensions. Here we have just 2 dimensions, but you can have 100, 500 dimensions that represent the variability of that face of a particular subject. We do the same for a different subject. So we construct this kind of within matrices that represent different subjects. And then we also estimate the variability between different subjects. So we construct, we apply linear algebra to construct this kind of within variability and between variability between different subjects. And we use that kind of within and between variability to construct also a linear projection, but a linear projection that is the best in linear terms, as a linear projection is the best to discriminate between subjects. is the best linear projection from the input faces that once we project, after we project in the projected space, which is a space also of a smaller size compared to the face images. In that projected space, the discrimination is optimal for that linear transformation. And as a result, the application of this LDA, this is equivalent to applying LDA, linear discriminant analysis, directly to the input face images. By applying LDA, we obtain much better results in biometric verification or identification compared to PCA. So LDA usually generate results in much better results compared to PCA, the previous eigenfaces. This approach is called also Fisher faces, because this LDA projection is also called Fisher discriminant analysis. So we have these eigenfaces, kind of seminal first popular work on face biometrics, which was clearly advanced with these Fisher faces. So now in the second generation of methods, we are now in the 2000s. So it's kind of an evolution of these linear projection methods, basically from an input face represented as a multidimensional vector, simple vector consisting of all the pixels in the input image. We apply a linear projection, and then we compare after we have projected using simple measures like Euclidean distance. So in the second generation, it's a kind of evolution of both the projection and how we compare, what kind of metric we use to compare to projected faces. So instead of linear projection, we use different kind of subspace methods, and we also use different kind of metrics to compare the vectors. So one popular method in the 2000s was sparse representation. In the sparse representation is a different way to project, to use subspaces, but instead of a linear approach is using different kind of subspace representation. So let's say we're not going into the mathematical details, so just to give you an intuitive idea, we can use this image. So let's say we have an input face and we have like a collection of a big collection of faces. That this big collection of faces kind of represents the overall population that we have in our problem at hand. So this can be millions of faces, there can be thousands of faces, so but it's representative of a population. So think that each one of these faces is one point here in this axis. So when we have a face as input like this one, we will try to find one or more of the faces here that are similar to the input face. So you can see here that in this case just one of them is very similar, but we can have 2, 3, only a few, not many of them, and this is the idea because of sparse because we have like a representation that with just a few numbers we can represent kind of well the input data, just with 2, 3 numbers here which represent the indexes of our reference data set, and then we have like a representation that is not exactly the same but it's similar. What is the difference between our representation and the input? So in this example you can see here that the difference is in this region, the eyeglasses. So what we code is the very few indexes that select just a few images, 1, 2, 3, very few, and this is very cheap to store. This is very small data, and additionally we also stored, in order to represent completely the input, the amount of information that is different with respect to the initial. In this case would be that region, and this region usually is only a small part of the face that can be stored in a compressed manner. So basically we represent the full image just with 2, 3 very few elements plus like a difference image. This works really well with this kind of face image. If we want to do the same for like a random image, then we may find some few of these elements, but then they will have to really store as difference image a lot of information. And this way the sparse representation will not be useful at all. So the sparse representation is very useful when we have a specific object like a face that with a number of not very big thousands of image can be represented in addition to the difference image. So this is kind of the overall idea. This is one extension of this subspace method. The subspace was represented by this collection of faces, and then also in 2000s there was big efforts in improving the way we compare the faces after the projections. Let's say we have a projection like linear projection like eigenfaces, Fisher faces, or even the previous sparse representation, any kind of transformation that takes like a segmented face and projects it to a subspace of smaller size, which is discriminative, and then we want to compare. So suppose this x, y, and xy are two different faces after the projections. This is the two different feature representations. And here we have a matrix. This is vector, a matrix. That is the matrix by which we define our distance. This is, if you have studied basic pattern recognition, this is a mathematical expression of Mahalanobis distance. But there are other ways. In fact, if this M matrix is the identity matrix, then this becomes Euclidean distance between the two vectors. But don't worry much about the mathematics. Basically, the idea is face, project to a subspace. This is a smaller size. We have a feature vector, and then feature vector. We have the Euclidean distance, and instead of Euclidean distance, we can do something more sophisticated in order to compare them, to compare the two feature representations in different ways. One way to do better, to improve the matching, is by introducing statistical information about the genuine distribution or made distribution, and impostor distribution, non-made. If we model properly, this is a distance score. This is what we call the distance. The lower the distance becomes a made comparison or a genuine comparison in a distance axis, and non-made is an impostor. So the higher the distance, the higher the probability to be an impostor. So we can use some statistical information that can be obtained from a development dataset with a development protocol, and based on that statistical information, let's say the mean and variation of the genuine distribution, mean variation, and even some other parameters of this statistical distribution that can be used to improve the way we compare the features. One way of that is by applying Kullback-Leibler divergence of other statistical methods. So just the take-home message, if we exploit any statistical information that we have about our problem, then we can improve the way we match. So this is an additional method, an extension, applying this idea of improving the metric to compare different features by Tuckman and Wolf. This is kind of approaching the state of the art now. Tuckman and Wolf are two important names that you will see afterwards. They were the first two to really apply deep learning successfully in face recognition. In this case, you have two input phases. First, there is a face detection, segmentation, alignment. So we have the feature vectors. So by linear projection or subspace projection. So and then those two feature vectors, this is kind of classical, and that was kind of a standard even in first generation. So in this case, the key modules that really improve the performance with respect to previous works, this we are here in 2009, is this improved comparison of the feature vectors. So there was a kind of normalization of these feature vectors in terms of statistical information, combining multiple approaches, and then applying a specific classifier, SVM classifier. So this is a way to really improve, instead of just a basic Euclidean distance between these two feature vectors, is applying kind of normalization, a statistical combination of multiple scores, and then classification. And then for a very popular database called LFY, this is labeled faces in the wild database. This is a really hard face database because it includes face expression, emotion, pose, variation, very natural. This is because this W in the wild, labeled faces in the wild, very popular in face biometrics. The accuracy was around 90%, very good accuracy overall. This is 1 minus equal rate in percentage, so almost 90% accuracy by Tuckman and Wolf. And there were some additional improvements, but mostly incremental. You can see that results in this database using exactly the same protocol defined also in LFW, in label faces in the wild, were around 90%. And this is basically an improvement of the distance metric. This is distance metrics learning in order to really do better in comparing the feature vectors, where the feature vectors are exactly the same, just linear projection or subspace projections. And then we enter the third generation. Remember here, just basic linear methods to project, not considering discriminant information, considering discriminant information, differences between different subjects, then better subspace methods like sparse methods or other linear subspace method, and then we improve the matching, we improve the Euclidean distance to more sophisticated methods, including statistical information, and then we arrive to the third generation deep learning around 2012 and 2015. So even less than 10 years ago, there was the deep learning revolution applied also to face biometrics. So this is one of the first works, deep face, that applied successfully deep learning using a convolutional neural network. I'm sure you have heard about CNNs by Alvaro and in other courses in this master. So in this case, applied to face recognition, the first application, successful application, was here, deep face. In fact, this is also authored by Lior Wolf, the one that we saw before, same author that we saw before in one of the previous highlighted works. In this case, first, before applying a CNN, the authors proposed to segment, to align the face, and once they had a well-located face, even with an active model representing the full shape of the face, afterwards they applied that CNN, applying different filters, different layers, in order to find a representation in a space of 400 dimensions that represented best in terms of discriminative information the face. It's basically as the first generation and second generation were linear methods, basically projection to linear subspaces. In this case, is a non-linear projection, and the non-linear projection is represented by several layers in which various convolutions are performed, and those layers and convolutions are trained to be or to generate a representation that is as discriminative as possible using an iterative optimization process to train the deep network. Why deep? Because we have several layers here that we have to train. How do we train this kind of network? We need really million images. For example, in this case, in this particular work, they use 4 million images from 4,000 subjects in order to estimate all the parameters in the network. Usually we have also millions of parameters in the network that we have to train. And you can see that the performance, best works, second generation were around 90%. We can reach here 97, 98, 99% performance in a very difficult database. So really excellent performance. And then in the last 5-6 years, there have been many different works really describing variations on this architecture based on a standard CNN. For example, multiple CNNs combined together in parallel, one CNN for different regions, like one CNN for the eye region, another CNN for the full face, another CNN around the mouth, and then combining the different CNNs in different ways. And in this way you can generate even better performance. From all the developments in deep face recognition, I want to highlight VGG face because of two things. First, it's publicly available, so you can just search VGG face, and then you can find the author's web, and you can download it. So you can play with it in Python or in other programming languages. It's the performance is very good, so you can see in this benchmark, so performance is more than 99%, so equal rate less than 1%, trained with 2 million faces, and the database called VGG face also it's also publicly available. You can get it. 18 layers, millions of parameters already trained, so works very well, publicly available, and it's widely used in the community for research and even as a basis for commercial systems. And another trick used here is that for training the network, the authors used a special kind of loss metric. So in order to guide the training of the deep neural network, they use what they call triplets. Triplets is 3 samples from 2 from the same person and another one from an imposter. It's basically using 2 kinds of comparisons, genuine comparisons and imposter comparisons. A genuine comparison will be between an anchor A and a positive sample. Anchor and positive means this is a genuine comparison. Anchor and negative, this is an imposter comparison. So by using millions of genuine comparisons in combination with imposter comparisons in an iterative process, they train the network to be to improve the performance, to have the best performance possible in a verification task, in an authentication task. And that's a novelty that previously not all systems use this kind of triplet based with 3 samples in the training. Also, in terms of tracking the state of the art, the main evaluations and the main benchmarks are from NIST, similar to the previous biometrics. And there have been NIST evaluations in face since the 90s, since more than 20 years ago. The most important ones are called FRBT, face recognition vendor test. This is one example, but every year more or less they have one of such tests. This is the kind of images that you can find in some of the tests, but they have several different tests with several different quality scenarios, and even multiple biometric benchmarks combining face with other biometrics. This is kind of high quality for NIST, and this is kind of some examples of low quality. So in typical evaluations, you can find system working at more than 97%, but usually when you, even for the best systems, when you change to this kind of wild images with low contrast, pose, illumination, shadows, and so on, then identification has lower performance. But anyway, very, very good, always higher than 90% for best systems. So as a summary, you have seen that we started with eigenface, Fisher's face methods in the 90s, then linear subspace methods and metrics learning 2000s. Now we are in the deep learning area. This means we have also evolved and grown exponentially in terms of the size of the data sets used for training, from hundreds of images to really millions and thousands of millions of images, and also the computing power needed to really train those networks has grown exponentially. The good thing here with deep learning is that for application, once the networks are trained, so for inference, so for using the networks already trained for verification, then they are very fast. You don't need that much computing power. Some examples from results from NIST, early results. This is, I think, the first NIST competition phase. You can see 93. So again, faces were published in 91. So you can see Fisher faces were published in 97. And this is, I think, accuracy verification rate for a given false acceptance. So if we fix false acceptance, then the verification, this is error rates, false rejection rate for a given false acceptance. So we fix false acceptance and we evaluate which is the false rejection. So we see that false rejection was huge for a small false acceptance, and for the same false acceptance, as the technology was evolving, then the errors, the false rejection errors, were almost inexistent, and that was even before deep learning entered into play. So what's next? So deep learning has really overcome many of the challenges. So face recognition is now applicable in almost all applications that we had in mind, for personal recognition in smartphones, for large-scale identification in forensic systems. But still there are some problems or some challenges that face biometrics has to deal with. For example, extreme pose. If we have big pose variation between enrollment and test, it can pose some difficulties, and not all systems work very well, even the best deep learning systems. Illumination can be a problem, big expression changes, aging can be a problem. Age, for example, for children or for old people, then face recognition system may not work as good as with people and mature people. Low resolution can be a problem, occlusion can be a problem, and other factors. So there are some variability factors that can be improved in implementation for biometric. So you can see here, for example, different conditions that we can find. Let's say this is good quality, this is challenging quality, and some databases available for research have these kind of conditions labeled, so we can play with them and then evaluate different systems or different approaches on different conditions. And this is a good way to really advance the research towards more robust results in challenging conditions. That happens also in NIST. NIST had a specific test in one of the NIST evaluation for face biometrics that was called the good, the bad, and the ugly. So there was the good, the bad, and the ugly NIST competition, where they tested nice or good quality images like the previous ones in the previous slide, bad quality, that is with illumination, artifacts, distance, and so on, and then really, really ugly. So there was a face, but the quality was the worst. But still, there was a face. So it was perceived as a face by a human, and a human could recognize that face, but extremely poor quality. And you can see here that with a fixed false acceptance, the accuracy, and this is the verification rate, was good, was almost 100%, so good accuracy, and the accuracy was extremely degraded for ugly. So this is kind of the biggest challenge in face biometric, to be more robust against poor conditions of quality. Aging is a problem. Are we able to really match a growing face across many different years? This is something that is being studied, especially in forensic applications, to identify people when there is a big a lap of many years between reference and test. And there are also methods for correcting the pose. Let's say we have different pose, we can detect the pose, so we can, for example, align based on an active model the different areas of the face, and then align to a reference orientation, and then based on that we can perform the recognition in much better conditions. Or we can perhaps sometimes estimate a 3D intermediate face in order to normalize different poses. That's also a topic of research. Not many commercial systems do this, so a robust deep learning based approach can overcome to some extent using just data-driven learning, not explicitly aligning this kind of pose. Man can have similar performance and even better performance than this kind of alignment-based face approach. There are also risks and vulnerabilities in face biometrics. For example, one can use a mask or other procedures to try to fake a face recognition system, and there is a lot of research in detecting those fakes and preventing or detecting or developing counter attacks to this kind of attacks. And this can be done at the sensor level. So perhaps the sensor can detect that this is not a skin. So this way we can discard this input face, or the face system can have a software module to really detect that this is not a natural texture or face. So we can have this kind of sensor hardware-based approaches or software-based approaches to detect these fakes and then do fake detection. And last, just a few slides on how additional information can help. Additional information found in the face or around the face can help in biometric identification. What is called soft biometrics. Soft biometrics is any kind of biometric information that is captured, but it's not discriminative enough to enable identification by itself. But it can help if combined with hard biometrics. Hard biometric is fingerprint, hard biometric is iris, hard biometric is face, because by themselves you can detect a person. Soft biometric, for example, can be age, can be gender, can be any kind of information that can help in identification, but it's not enough for that identification. So in this example, I'm going just to put a few slides about this. Some of these soft biometrics that are sometimes used for improving face recognition is gender, ethnicity, age, glasses or not, mustache, birth, and others. Some commercial software packages like Face++, this is one of the best now in the commercial application for face recognition, and other artificial intelligence tools like Microsoft Cognitive also incorporates both face recognition and automatic tools to extract this kind of soft biometrics with a face using Face++ of Microsoft Cognitive, you can generate gender, ethnicity, age, and so on. In fact, in the school at UAM, we conducted a comparison study studying the soft biometrics generated by these two commercial tools, and then compare them with soft biometrics obtained manually using the LFW database that we mentioned before, that is commonly used in face recognition. So we applied manual labeling, automatic labeling, and if you are interested, I can provide you some additional work. So for example, here you can see that from all the images we can extract easily the age, the ethnicity, gender, and so on. And this can be labeled as a ground truth manually using a tool that we develop here, and we can compare this with automatic labels. And in fact, in the study that we conducted, we observed that the performance in generating this soft biometric is not perfect, of course. In some cases, if the image is difficult enough, like here we have occlusions, we have glasses, we have more occlusions, then the performance here to generate those soft biometrics is not perfect. It's in most cases around 90-95% for this kind of general purpose database. How are these soft biometrics used commonly in a kind of multimodal system? We use face. From face we extract features. The features extracted can be based on BGG face, for example, the deep network, which is very good. So the output of BGG face can be a representation of 1000 features or 4000 features, depending on the level at which we extract the features in this deep network. Then we apply matching. Matching can be simple. If we apply here a deep network, then matching can be just Euclidean distance. No need to incorporate sophisticated metric learning here. If we applied extracted features using a deep network, we compare the features from a database. We have a score, similarity score here. And then at the similarity score, we can combine with, from the same person, we extract one or several soft biometrics. We use those soft biometrics and compare them with the soft biometrics stored in a database for the same person we are comparing. And then we combine that. And there are several different ways to combine. We will explore different fusion combination ways in another lecture afterwards. And that's all.